Okay, so we're going to have a look at the ability of group 7 to act as reducing agents and to act as oxidizing agents. Now, first thing you have to really get clear in your head is it's the group 7 halides themselves which can act as reducing agents, and it's the group 7 halogens, okay, so not the ions, the halogens themselves which can act as oxidizing agents. So get that clear in your mind first and foremost, because if you confuse those two things, you really are in a bit of trouble. Right, so let's look at the halides, and when we talk about the halides, what we're referring to are the halides as their ions. So you're talking here about chloride ions, bromide ions and iodide ions. Those are essentially the ones that we will look at. So when you talk about them behaving as reducing agents, you talk about the ions, not the actual elements such as chlorine, bromine and iodine themselves. So if they're going to act as a reducing agent, this means that they themselves have to get oxidized. Alright, so things can only behave as reducing agents when they themselves donate electrons. And if you think about that, why would that rule out chlorine behaving as a reducing agent? Well, that would have to go to chlorine with a positive charge on it. The amount of energy needed for that, whether it's chlorine or bromine or iodine, doesn't really matter. The amount of energy needed for that to occur is just much too vast in order for it to behave as a reducing agent. And you won't see chlorine as a positively charged ion, or bromine, or indeed iodine. Okay, so this thing has to be oxidized, and if you think about it, can chloride ions themselves lose electrons? Well, of course they can. And if a chloride ion loses an electron, it turns into chlorine. Okay, plus that. You could also, I suppose, more commonly write that as when chloride ions get themselves oxidized, or in other words behave as reducing agents, they turn into chlorine gas. Like so, you can see it has been oxidized. The electrons on the right hand side of the arrow are now separate from the chlorine on the left hand side of the arrow. Now your task is to explain why first of all these things can behave as reducing agents, and we can see that it's because they have the ability to lose electrons and therefore be oxidized. But you'll also be asked to, why is it that iodide ions are stronger reducing agents than bromide ions, which are stronger reducing agents than chloride ions? So I've kind of gave it away there a little bit, in that the order of strength of reducing agents is that to that to that. Now, why is that the case? Well, if you think about it, in order for something to be reduced, it has to lose electrons. So we're basically saying, if this is in their order of reducing power, okay, iodide being the greatest, therefore what we're saying is that iodide can have its electrons removed or electrons lost most easily. Okay, in other words, with least energy. Okay, so that is why iodide is the strongest of all the reducing agents. The next question, I guess, then is, well, okay, if it is, why is iodide the strongest of all of these in terms of it being a reducing agent? Well, where does the electron in iodide reside? Where does the outer electron, the electron that it's going to be losing, is its very most outer electron? Okay, so that is why, as you see on the screen now, the larger the halide ion, the easier it is for it to donate electrons, in other words, for it to be oxidized. Okay, and that's because its outermost electron is further from the attraction of that nucleus, more shielded from it by the other electrons. Okay, and the attraction is weakest. Why is that the case for iodide? Well, I think it's, hopefully you can kind of work this out yourself. The outer electron in iodide ions are going to be much further from the nucleus and will experience much greater shielding than the electrons in, let's go to chloride ion, the outer electron in chloride ion, which is going to have a much stronger attraction felt from the nucleus. So the ease with which this electron can be removed from an iodide ion is much greater than the ease with which this electron could be removed from a chloride ion. Therefore, iodide ions are better at losing their electrons. Therefore, iodide ions are better at being oxidized, and therefore they are better reducing agents. Now, now that you know how to explain that to an examiner, how can you show it? Well, you show it through your displacement reactions. So, for example, if we took, let's say, chlorine, okay, and okay, so if we took, let's say, the halide ions, so the way that you're going to show this or illustrate this is via the reaction with concentrated sulfuric acid. And basically what you're going to do is you're going to map the change in the oxidation number of the sulfur and sulfuric acid from +6 to whatever it goes to. So the stronger the reducing ability of the halide ion, the lower that number will go. It goes right down with iodide ions, right the whole way down to -2. That's the lowest we get. And if you think about that, that's a -8 change in the oxidation number. That's significant reduction that's taken place there. But we'll look at the individual reactions, okay, and we'll see how the different ions cause different amounts of reduction, or maybe no reduction at all. So let's look at our reaction first of all of sodium chloride with concentrated sulfuric acid. Okay, and we'll write the products. The products of this are sodium, hydrogen sulfate, and we also get hydrogen chloride. Now if we do all of our oxidation numbers the whole way across there, and hopefully you're following me when I'm doing these and know where they're coming from. Okay, +1 for the hydrogen, -1. And if you look at that, there is no redox happening in that reaction at all. So what we're essentially saying here is that this chloride ion has been unable to reduce the sulfur in the sulfate ion and the sulfuric acid. And sulfur and sulfuric acid is relatively easy to reduce. So if you can't reduce that, then you're nearly not a very good reducing agent. And all you would see here are good old faithful Stevie fumes, which is the hydrogen chloride. Right, the second reaction then is with bromide ions. We'll just use sodium bromide, that's one that's used in texts all the time. So the oxidation numbers of everything there is exactly what we had in the previous reaction. Now this time we will get a variety of products produced. We will get the same products produced that we had in the previous one. We'll get some hydrogen bromide, we get some sodium hydrogen sulfate, but this reaction continues beyond that point, okay? And we also get some bromine produced. We will get some sulfur dioxide, SO2. We'll get some water produced, not a big deal, water in this instance, okay? So all of those things end up being produced in this particular reaction. Now let's have a look if there's changes in oxidation number. So we'll do the same. Everything's the same there, but I just want to bring emphasis to the two things that are going to change. So the sulfur at +6 and the bromide at -1. So bromine here is 0, okay, in elemental bromine. The sulfur here now, each of the two oxygens here are -2, so that in total is -4, okay, for the two oxygens. The overall charge on the molecule is 0, so the sulfur must be +4. Okay, so if we look at that, the sulfur has gone from +6 to +4, so it has been reduced. And the only thing that has been oxidized in this equation is the bromide ions to bromine. So therefore the bromide, the sodium bromide, the bromide ion in particular, is reducing the sulfur from +4 to +6. So up here it was +6, it stayed at +6. Down here it has gone from +6 and the bromide ion has brought it to +4. So there's a bit of reduction going on there. Okay, let's look at the next reaction that we would use, which is an iodide ion, again with concentrated sulfuric acid, of course. Okay, and this time we will get a mix of products. We will get iodine molecules, we will get hydrogen sulfide gas, and we'll get waters as well. Not a huge deal, but anyway, we will get them. Alright, I haven't balanced these equations, alright, but okay. this is -1, sulfuric again is +6, just doing the relevant ones. Iodide ions have gone from -1 to 0, so of course they have been oxidized and therefore are behaving as the reducing agents. Our sulfur has gone from +6, okay, right the whole way down this time to -2. Remember, the two hydrogens are +1 each, so that's -2 in total. The overall charge of that compound is 0, so you have -2. So here we're going from +6 the whole way down to -2 for the sulfur in this instance. Okay, so, and that's that hydrogen sulfide, that's that sort of rotten egg smell that you would use in your description. Okay, if you were saying what your sort of your observations would be here. Okay, you will also get in this reaction the same as well. You will get some of that pungent sulfur dioxide given off as well. Okay, you will also get in this one some sulfur, solid sulfur, which is a yellow substance, so you would probably describe that. I'm just showing the products that are the most significant in terms of the biggest reduction in the oxidation numbers, which is of course right down to -2. So you can see therefore we have not only back here have we talked about why one was a better reducing agent than the other, but now you have got the reactions, and these reactions are in your notes. You have to be able to write the balance symbol equation for the reaction of the chloride, bromide and iodide ions with sulfuric acid. So please make sure you can do that. You can explain why iodide ions are the strongest reducing agents, and remember it's the halide ions that are reducing agents, not the halogens themselves. Okay? Okay, so good. Okay, so if we then go ahead, guys, to have a look at the strength of the halogens, okay? So remember, now I've changed my language. I'm talking about the halogens, which are the elements themselves. So chlorine, bromine and iodine are the ones you need to be aware of, and we're looking at their strength as this time as oxidizing agents. So we've moved away from the halide ions as reducing agents, we're looking at oxidizing agents. Now what happens to oxidizing agents? Oxidizing agents themselves get reduced, and if something gets reduced, it gains electrons. So let's look firstly at same as we did last time. Why is one a better oxidizing agent than the other? Okay, well, I'll tell you the chlorine is a stronger oxidizing agent than bromine, which is a stronger oxidizing agent than iodine. So not unsurprisingly, the opposite order as to the reducing agents, except the reducing agents were obviously the halide ions. Right, so let's look at why that would be the case. So when two things are battling over one electron, if we sort of pretend chlorine, okay, has a nucleus of course, and then it has 1, 2, 3 electron shells. If I was to compare then that to bromine, okay, of course it has a nucleus, but it is a much bigger atom. So if I was to say which one of those is going to win the battle for the attraction of this electron, it is going to be the chlorine, because its nucleus is less shielded from the electron that it's trying to gain than the nucleus of bromine. So up here we have a much stronger electrostatic attraction to the nucleus of chlorine than I have to the nucleus of bromine, and that stronger electrostatic attraction means that it will be better at gaining electrons, therefore it is better at getting reduced, and therefore my chlorine is my stronger oxidizing agent. So it's all to do with the number of shells, the amount of shielding, and the electrostatic attraction between the nucleus of whichever atom it happens to be and that electron that it is trying to gain. Now, how do you show that in terms of your chemistry and your equations and your observations? So this is where we use our displacement reactions. Okay. Now, so your displacement reactions, and you did these at GCSE, they're fairly straightforward. So chlorine maybe with aqueous sodium bromide. We know chlorine, so if we think about that's a bromide ion at -1, chlorine is 0. So chlorine, if chlorine is a better oxidizing agent than bromine, it should oxidize our bromide ion to bromine, because that's the only oxidation that it can. And if we did this in a test tube, you would indeed see that that's exactly what happens. Okay, we can balance that equation. And the reason we would see that happening is because we would start off here at colourless, and we would end up here with a sort of a brown orange solution. Okay, and that would be proof that bromine has been made from bromide ions. Remember, bromide ions have no colour in solution. Bromine does. We could do the same then for chlorine, just to prove that it's a stronger oxidizing agent than iodine. Okay, so, and we would see a similar, sorry, that's a Cl, a similar reaction, that we would get a much darker brown solution produced here, where the iodine, okay, has again gone from -1, sorry, that bromine above, I should have said, it's gone from -1 to 0. This is also gone from -1 to 0. Again, this solution over here is also colourless, and the brown tells me that I have made some iodine, therefore proving that the iodide ion has been oxidized to iodine. And the final one that you could use there, sorry, is to prove that bromine is a stronger oxidizing agent than iodine. Okay, we would put bromine water, a solution of bromine, into a solution of aqueous sodium iodide again, colourless solution. Okay, and that will, if oxidation of the iodide ion takes place, it will be oxidized to iodine, and that's exactly what will happen. You will see a brown solution forming, proving that iodine is indeed present in there, and therefore the iodide ion has gone from -1, it's been oxidized to 0, and the only thing that it's done that is the bromine, which has gone from 0 to -1, it has been reduced, therefore it's acting as the oxidizing agent. And that's the chemistry that you would need to be able to use to describe and to show, to prove that your theory from the previous page here is in fact correct. Okay guys, I hope that helps you talk about the strength of the halide ions as reducing agents and the strength of the halogens as oxidizing agents.